Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. You'll find videos on topics in a lot of your math courses, whether it's algebra, stats, trig, pre-calc, calculus, differential equations, linear algebra, and more advanced topics as well. If that's something that you would find useful or interesting, please consider subscribing and watching a bunch of our videos, because that will help us grow. We're pretty small at this point, and we'd like to reach a larger audience. In this video, I want to take a look at one of the integration techniques you'll find in your Calculus 2 course called the shell method. In this particular one, I want to take a look at rotation about the y-axis. I'll also create videos where I look at, okay, well, what if I rotate about a vertical axis off the y-axis, or the x-axis, or a horizontal axis off the x-axis. So I'll look at variety of instances, but what I want to do in this particular video is look at particularly rotation about the y-axis. Okay, so let's take a look at how this works. Suppose I have a graph of a function y equals f of x, something along these lines, and I take that, the area bounded by the graph and the x-axis, and I rotate that about the y-axis. Again, you imagine that this is spinning around, creating this three-dimensional solid. In this particular case, what that would generate is what you could imagine looks sort of like a bundt cake, if you know what that is. And this would, of course, be just the back half of it. I can't really draw outside of the board here, but I can kind of give an idea of what it's going to look like. It's essentially this three-dimensional solid with some sort of a hole in the middle, or some sort of like a cavity kind of dug out in the middle of it, right? Well, what I want to do is I want to be able to create a formula to generate or compute the volume of this. Well, think back to whether it's area under a curve or other geometric formulas for area, volume. If I want to use an integral to compute that, what I have to do is I have to take this sort of complicated geometric object and I have to decompose it into simpler geometric objects. And then we come up with a formula for the approximate volume or area, surface area, whatever the case may be. And then we're going to, through a limiting process, turn that into an integral, which will give us the exact geometric quantity, again, area, volume, whatever you're computing. So let's look at that process. I'm going to take this object here and I'm going to decompose it using the following basic geometric shape. I'm going to look at what are called nested cylindrical shells. So what I'm going to do is I'm going to take, you could imagine that this isn't the best sort of object here to use, but I think it kind of gets the point across. So think about like a paper towel roll, right? So what I have is I'm going to approximate sort of each of these as like nested paper towel rolls, right? So I've got this, it's a cylindrical shell, it's got a hole in the top, hole in the bottom, it's got a width to it, and think of these as, like down here, it might be that tall, then this tall, then this tall, so on and so forth. And you can imagine that this here is sort of just the back half of one of those cylindrical shells. And that is going to be my basic object that I'm going to decompose this into, is this collection of nested cylindrical shells. Therefore, if I computed the volume of, again, that sort of basic geometric shape, then if I were to take the sum of all of those volumes, of all of those shells, that's going to give me approximately the volume of this entire three-dimensional solid that we created through a revolution. Of course, it's not exact because, you've got this error of maybe the shell sits a little bit above, a little bit below, but it's going to be a very good approximation. Again, we will make the approximation exact as we go through the process. Again, the volume is approximately the sum over all the shells of the volume of each cylindrical shell. Okay? Well, what I have to do is I have to take one of these cylindrical shells and come up with a formula for its volume. Now, we have formulas for the volume of a shell or volume of a cylinder, right? 2 pi RH. But this one, since it's a shell, it's actually going to be the difference of the outside versus the inside. So I'm going to have a difference of terms, but what I want to do is I want to, in order to be able to turn this into an integral later on, is I want to come up with the volume of this in one term. Okay, I don't want to have the difference of terms, like the difference of the outer cylinder minus the inner cylinder. I want to have the volume of the entire piece in just one term that's all products multiplied together. So here's how I do this. Imagine I was to take, again, one of these cylinders, and I was to take a pair of scissors and just slice it along there, okay? And then slice it along, and then I'm going to unroll it, okay? So again, I'm going to take a slice here and cut it all the way down. Then I'm going to unroll it. What that's going to give me is going to be a shape like this. So it's not going to be exactly this rectangular solid, because when I unroll that, this is actually going to have a little angle to it. But again, we're going to take a limit of that, so the width of this thing is actually going to end up going to 0, so that doesn't really make that big of a difference. And again, we're just using approximations here anyway. But let's go ahead and let's label some parts of this. So as you can see, let's take this shell and let's compare it with this one over here. Well, what do I know? I know that the height of this, so let's label that the height of this here is h. Well, that would be the same quantity as right here. And notice that the height is the distance from the x-axis to the point on the graph, which really is just the function value. So I'll say that the height is actually f of x. Okay, so then I also would know, let's say, the radius of this. So let's say from the center of that inner cylinder to here, let's call that r. Hopefully you can see that, so that's r. Well, what is that distance? Well, again, that's going to go from, say, the y-axis out to a point on here, and let's say that's x. So the distance from here to here, say the inner part of the cylinder, so let's call that x. And then, well, the width of this is, say, delta x. So let's say the width of this is delta x. So that means this distance here is delta x. Now let's take that and let's translate it over to this other object. Well, the height, again, is this distance, so that's going to be f of x. The width of this is going to be delta x, so that's the width. And then we also have the radius is x. Well, what I need is this length. Okay, so I've got the width, I've got the height, now I need this right here. Well, notice that this distance all the way around is actually the circumference of that circle. So the circumference is going to be 2 pi times the radius, so 2 pi x. Therefore, the volume of a cylindrical shell is 2 pi x, f of x, delta x. It's the product of those three dimensions, right? The volume of a box is length times width times height. Therefore, the volume of the original object is approximately the sum over all shells. Again, this is just an informal way of writing this. The sum over all shells of 2 pi x, f of x, delta x. And of course, that's not a quantity we're going to compute directly, but this is an example of a Riemann sum. So what do we do with Riemann sums? Well, to make it exact, to make this equality an equal to sign, we are going to take the limit of the expression here, so the delta x, I'm going to take the limit as that quantity goes to 0. And that's going to give me my exact volume. All right, therefore, the exact volume is given by the limit as the quantity delta x approaches 0 of the summation over all shells of 2 pi x f of x delta x. And of course, the limit of a Riemann sum leads to the Riemann integral. And this is equal to the integral from a to b, where again, a to b are your limits of integration, which should be clear from the context, and we'll talk about that as we go through. And then this would be 2 pi x f of x dx. So this right here is the formula we will use when we decompose a three-dimensional object generated by a revolution using the shell method. So let's take a look at two examples of computing a volume using the shell method. Okay. For example, first example I want to do is going to be a graph that resembles sort of the motivating example that I did. So let's take a look at the function f of x is equal to sine of x squared on the interval from 0 to the square root of pi. Now, if you graph that, again, you're going to generate a graph that looks very similar to the motivating graph that I used. Okay, so let's see how this works. So again, I take the area bounded by the graph and the x-axis from 0 to the square root of pi. I spin that about the y-axis to create this three-dimensional solid of revolution, and I can compute the volume using, again, the shell method. Well, what I like to do is I like to put in a typical, what would the schematic diagram look like for if I was to put a shell in here? So what I'm going to do is do this line and then this line. This line right here that goes from the axis of rotation to the graph would be the radius of your shell. And the line that goes from the x-axis up to the point on the graph is going to be the height of the shell. And over here, again, let's record what would R and H be. Okay? R, the radius, would be from 0 to whatever the x value is. H would be the height, that's going to go from 0 to the point on the graph, which would be the function value, or in other words, sine of x squared. Okay. Now, let me go back to this function right here, this equation right here, and let me just slightly generalize that, right? The slight generalization of this is I'm going to say the volume is going to be the integral from a to b of 2 pi r h dx. The radius is not always going to be x. The height is not always going to be f of x. In this current video, it will be, because again, I am rotating about the y-axis. If I was to rotate about a vertical line, then the radius would be something different. The height could be something different depending on how I orient my graph and what I'm rotating about. So just in general, this is your formula, but in this particular case, 2 pi x f of x is your integrand. Okay, let's go ahead and run through the computation then. The formula for the volume is integral from 0 to the square root of pi. Okay, your limits of integration are determined by your graph here, so from 0 to the square root of pi. And then it's going to be 2 pi x f of x, so sine of x squared, and then dx. All right. While I clean up the other side of the whiteboard so I can continue working over there, see if you can work ahead and compute that integral. I'll work through the steps over here, but see if you can, go ahead and try that on your own. If you're still working, go ahead and pause the video and then resume it when you're done. Okay, let's go ahead and compute it. If you look at the structure of this integrand, notice that it is a product of two expressions where one of the factors is a composition and the function that's inside the composition, its derivative, appears as a factor. Therefore, u substitution is appropriate. U is the inside function, so u is x squared. Du would be the differential of that, so 2x dx. And then since this is, of course, a definite integral, we have to change our limits of integration from 0 to the square root of pi, which is on the x-axis, to something on the u-axis. So u of 0 is 0, and u of the square root of pi is pi. Okay, therefore this integral that we started with is now equal to the integral from 0 to pi, and I've got 2 pi x sine of x squared dx, 2x dx is du, pi remains, and therefore my integral will be pi sine of u du. Okay. Antiderivative of pi sine of u would be negative pi cosine of u, where u is going to range from 0 to pi. So that's negative pi cosine of pi minus negative pi cosine of 0. And cosine of pi, remember, so cosine is the x-coordinate, pi is the angle, so if I rotate pi, That's on the far left-hand side of the circle. The x value is -1, so this is negative pi times -1, which is pi. Cosine of 0 is 1, so therefore negative times negative is positive, times pi times 1 is pi, so pi plus pi gives me a volume of 2 pi. Okay. Let's do one more example. Let's take the graph. Okay. This is y equal to x plus 1 on the interval from 0 to 1. So that would make that 1, make that 2. And I want to take the area bounded by the graph y equals x plus 1 on the interval from 0 to 1, and I want to rotate that about the y-axis and then compute the resulting volume. Now, let's talk about how we could do that, because I don't have to use the shell method. If I generate that, it's going to create, imagine taking a solid cylinder and then sort of drilling out this like conical section in the top. Well, if you think about that, and if I look at this as, say, a stack of plates, or a stack of discs, going from here to here, I could use the disc method. And then going from here to here, I could use the washer method. Right? So just a stack of plates and then a stack of washers. And therefore we could compute the volume by computing two integrals, which is again not very efficient, but I could use that as disc method, washer method. However, the shell method allows me to set this up as a single integral and compute the volume more efficiently. All right, again, let me put in sort of my schematic for a typical shell. So little line segment from the axis of rotation to the point on the graph, and then from there the point on the graph down to the other axis. So again, that would be my R, that would be my H. So then let's list what is R equal to, what is H equal to. R is the distance from the axis of rotation to this point here, and that would be from 0, say, to X. H goes from the horizontal axis up to the point on the graph, which is the function. And then now for my limits of integration. Well, what do my limits of integration go between? It should be fairly clear that it's 0 to 1, but let's see another way to look at that. What does the radius range from? The radius goes from 0 to 1. So therefore, the limits of integration go from 0 to 1. Okay? Therefore, my volume is the integral from 0 to 1 of 2 pi x plus 1 dx. So that would be 2 pi, pull that outside the integral, 0 to 1, x times x plus 1 would be x squared plus, no, not plus 1, plus x dx. So it's integrating a polynomial, use the power rule for the antiderivatives. We get x to the third over 3 plus x squared over 2, where x goes from 0 to 1. And I need just a little bit more space to go ahead and work that out. therefore, this would be equal to 2 pi times, if I plug in 1, I get a third plus a half. Plug in 0, of course I get 0. So this would be 2 pi times, well, a third plus a half, common denominator would be 6. So that'd be 2 over 6 plus 3 over 6, which is 2 pi times 5 over 6. Of course, 2 over 6 is going to leave a 3 in the denominator, so that's going to give me 5 pi over 3 for my resulting volume. So it'd be a good exercise to then compute the volume a different way. Like I mentioned before, use the disk method, the washer method, and make sure that adds up to 5 pi over 3. Okay, thank you for watching. And again, if you find videos like this useful, helpful, interesting, please consider subscribing, watch some of our other videos, and make sure you hit that bell notification for notifications for future videos, which will be coming very soon, and especially things like this where I'm going to do rotation about the x-axis and other axes as well. So thank you for watching.